All right. So, since we learned about trapezoids yesterday, here's a trapezoid. Is this an isosceles trapezoid?
No.
No. How do we know?
90-degree angle.
There's a 90-degree angle here, and there's not one over here, right? Because it should be symmetric if it's an isosceles. Okay, so we are supposed to find x and y. Now, anytime you see a trapezoid, I do think it's going to be helpful to do something like that. Try to figure out, does it have one triangle on the edge, or does it have two triangles? In this case, there's only one. Now, are there any pieces of x that we know already? The 6, right? This edge is going to be exactly the same as this much of x, because this is a rectangle, right? This is a rectangle. So this much is 6. All right. Now, do we know anything about the right triangle besides the fact that it's a 30, 60, 90? Because if we only know that it's a 30, 60, 90, we're not going to be able to do anything with it. Yeah, Lily. We do know the height, right? Because this edge right here can carry over this way because it is a rectangle. So we know now that this is 5. All right, so let's put on our sides of our 30, 60, 90 right triangle. This would be x, this would be x root 3, and this would be 2x. Okay, so I know that the x is 5, so therefore y is going to be 10. Yay, I found y. Now, this portion of the bottom edge is going to be 5 root 3. And so therefore, the x value is sort of a combined number. It is a piece that is 6 together with a piece that's 5 root 3. You're going to start seeing more of that. Leave it like that. That's really the most exact answer. Could you type that into your calculator and get a decimal and get a more exact value? Sure. But this is actually the most exact because you're not rounding it. So we'll just leave that. So don't forget those special right triangles. They're going to keep showing up. All right, so let's talk about a kite. We actually saw kites quite a bit. I'm going to get out my toys here. We saw kites quite a bit in proofs, didn't we? So if I have a kite, one of the things that is always true about a kite is that it is a quadrilateral. Oh, that one's not magnetic. Okay. It is a quadrilateral that has 2 pairs of consecutive congruent sides. All right. Well, that's a lot of fancy math words. I like to explain it as 2 isosceles triangles that share the same base. Right? Because isn't this just 2 isosceles triangles? So let's write that. So let's do that. So it's 2 isosceles triangles sharing the same base. So this would be that shared base right here.
Isn't it an equilateral triangle?
It could be, like, I would say one of them could be, but it doesn't have to be. All right, so sure, the way this is drawn, it kind of looks like the top one is, but it doesn't have to be. Let's see. If I draw in the other diagonal, there's also some other symmetry I want you to see. If we draw in this diagonal, or this spine of the kite, do you see that there are triangles on the left and on the right that are exactly the same? So there are 2 congruent triangles in that orientation. But if we look at it as the 2 isosceles triangles, like this one here and this one here, these are not necessarily the same. In fact, usually they're not. So these two triangles are not necessarily congruent.
Would they be similar?
Not necessarily. But there is something. What would happen if we kind of shrunk this one and they were exactly the same? You're close. It would be a rhombus. So what's interesting is that a kite shares a lot in common with a rhombus. So let's think about that again. So here was, when we saw rhombuses, I used this as an example for the rhombus. And some people called it a kite. And I was like, oh, we're going to get to that. I like to use this as an example of a kite because it illustrates that they don't have to be the same. And most of the time, they're not the same congruent triangles. When they are the same, it is actually a rhombus. And that's where like a kite and a rhombus sort of like overlap in the Venn diagram, if you will. So the formal definition is two consecutive congruent sides. So these two are congruent, and then these two are congruent. So here are your properties. You've got two pairs of consecutive sides, and you've got the longer diagonal is the perpendicular bisector of the shorter one. That was something we worked a lot with in proofs. Let me illustrate that. So if I draw a kite here, all right, there's one diagonal, here's the other one. What happens is the longer diagonal is the bisector of the shorter one. So this and this will always be congruent, and these will always be perpendicular. Obviously, the long diagonal does not necessarily get cut in half, okay? Because those triangles are really different sizes. One pair of opposite angles are congruent. All right, that would be, let's see if you can figure out which pair of opposite angles that is. Is it the top and the bottom, or is it the left and the right? It's the left and the right, absolutely, okay? Because we did see that symmetry, that folding across the long diagonal. Yeah.
Are they bisected?
Great question, and yes. So the top, you could almost add that here. You could say that the top and bottom angles are bisected. Bisected by the long diagonal. And, you know, would you add that to this list of properties? Sure, you could. Or you could just remember that because of the symmetry, right? If you're folding it this way, then that means that this angle is going to match up with this one, and this angle down here will match up with that one. So sometimes that's not really listed as a property, but it is always true. Here is sort of your new hierarchy with everything in it. And as you saw, the rhombus and the kite will share some things in common. They both have perpendicular diagonals. And a kite with two congruent isosceles triangles is a rhombus. All right, so then let's see here. Let's try one out. So if you needed to find angle D, sometimes I think it would be helpful to draw in some diagonals, maybe figure out some, maybe look at the left-right triangles or look at the top-bottom triangles. There's a couple different ways to approach this. If you drew in this diagonal, what you know is that this is an isosceles triangle. So this top triangle, this is 124, this would be x, and so would this. They would have to be the same, because if sides are congruent, then angles are congruent. So that's one way to approach this. So, if sides, then angles. So 180 minus 124 is what, 56. So 2x equals 56. And so x is, what is that? 28. Thank you. So if this is 28 and this is 28, you could kind of do the same thing down below. If this is 80, then you know that this is 50 and this is 50. So angle D is 78. Now, I would argue that maybe this problem would have been faster if I had drawn the other diagonal. All right, but I wanted to show you that it could be done both ways. If we had drawn the other diagonal, we would have done this, and this would have become 62, and this down here would have become 40, and then we would have looked for this. Yeah?
Couldn't you also just add 124 plus 180, and then subtract that number from 360, and then divide that by 2?
Absolutely.
Okay.
So now we've just seen 3 different ways we could do it. So yeah, since it's a quadrilateral, those interior angles will always add to 360. So totally. We like that. We like the symmetry of these shapes. That gives us options. Okay. This is kind of a unique kite. So that's maybe the first thing I want you to notice about this. This is a unique kite. And I would say it's unique because of that right angle and that right angle. Yeah, Nika.
To find this one, would we have to do the 2 triangles, like the longer ones?
Yes. So I think on this one, what you want to do is to focus on the longer triangles. And so when you do that, focus on the longer triangles. It's a right triangle, and it's got an altitude drawn to the hypotenuse. I know this is an altitude because I know that these are all right angles. So this is an altitude drawn to the hypotenuse, which means we can use those theorems like altitude squared equals part times part, side squared equals part times whole. So here, we're going to use side squared equals part times whole. Side squared equals part times whole. Or, maybe in your homework, you have one where it's altitude squared is equal to part times part. Hold on, I see a hand. Yes?
Since the hypotenuse is equal to 13, can we automatically assume that it's a 5, 12, 13?
Good question. No, you can't. Because it could be a 30, 60, 90 right triangle that happens to have a hypotenuse of 13.
Right.
In order to know that it's a triple, you have to have 2 of the 3 to know.
Okay.
So this one, in order to solve this one, we would just do x squared is equal to 4 times 13. So x squared is equal to 52. And so x is the square root of 52. And then usually if you get radical problems, we just want you to go ahead and break that down. So 52 was 4 times 13. So x is 2 square root 13. That is not going to happen on every kite. but I did want to show you that that could happen, and that's something that we just learned in chapter 7. So, just watch for it. The reason it can happen is because these diagonals are perpendicular. So that happens to be the altitude. All right, so your assignment is 8-6. I do think that 8-6 is a step up in difficulty from the problems that you've had up to this point. Use symmetry to help you. Come with your thinking caps on tomorrow. I think tomorrow's lesson might be the hardest one. But I like it. We do a lot of proofs, but not proofs. They're not proofs, but we do a lot of proving. But they're not proofs. Okay?